Our speaker tonight is Dr. Benjamin Zitzer, and he's been a member of the Fort Wayne Astronomical Society since 2020.
2020.
And you've been a board member since when?
Shortly after.
Shortly after. So we'll say
Like
21.
21, probably, early
Yeah.
21.
Dr. Zitzer earned his PhD in physics from Purdue University in 2011. His thesis was gamma ray pulsars and pulsar wind nebula. That was really cool to me. I like that.
I did talk about this back a couple years ago.
From February 11th to 2015, he was a postdoc associate at Argonne National Laboratories, and I like to think of it as Willowbrook because that's where I was living when we lived near the Argonne National Lab, and so it's kind of a coincidence. We're almost neighbors. We were only separated in time and distance by 9 years, if you can believe that. Almost neighbors.
Like 30 miles too, something like that.
Yeah, that was no big deal. And from 2015 till 2019, you were a research scientist at McGill. You might or might not want to comment on what you did there. But currently, he's a systems engineer at L3 Harris, helping to design, develop, and deliver the next generation, the even more advanced weather satellites coming out of Fort Wayne. The two that are up there for NOAA right now also came out of Fort Wayne. We have the same weather instrument, one of those for Japan and another one for South Korea.
Yep.
And a couple other extras up there right now, just in case. So we have a very good history of delivering high performance weather satellite, and because I still think of myself as an L3 employee, beat out competition to get the next generation. So do a good job for us there.
Do my best.
So it's a pleasure to have Ben tonight to introduce cosmic rays, their history, along with some methods for detecting and areas of ongoing research, and perhaps even tell us about how we might be able to detect them as part of the Fort Wayne Astronomical Society. So with that, I think we'll turn it over to Ben.
All right.
And I'm guessing that we have to go find your presentation. Do we have it up already?
I think it got closed.
There it is.
There it is. Cool.
But we don't want that one. We want that one, don't we? And then if we can come back to the Zoom meeting, and then we'll share. And then we'll share like this one. And then share. Okay.
All right.
And you can deal with it because you're a professional. Thank you very much, Ben. Go for it.
You're just teeing me up to make a fool of myself, aren't you?
No, I don't think I have to tee that up at all.
Oh. All right. Thank you, Joe, for the very nice introduction. Always a pleasure to talk to you guys, and I'm happy we got a good turnout here. So I titled my talk Astronomy Without Light. So basically, I'm going to be talking about astronomy that does involve any sort of light detection. It's going to be detecting particles from outer space, basically. So I'm going to talk about cosmic rays and the methods of their detection. This is a subject that's near and dear to my heart. So just an outline here. What are cosmic rays? What are they composed of? What do they do? / why do we care? Why they're interesting? I always like to talk a little bit about the history of the field when I'm giving these sorts of talks. So I'm going to talk a little bit about the big milestones in the field of cosmic rays. Then I'm going to get into the methods of detection and talk about all sorts of different experiments of all sorts of different shapes and sizes. I think I will probably surprise some of you by that, but just like the variety of the different types of instruments there are. My personal experience in this field, and this is one of the things I was doing in Canada, by the way. And this is, I'm calling it Finding Treasure from Trash with Veritas, the experiment I worked on for a number of years. I'll close out by talking about just a few of the unsolved mysteries, the areas of ongoing study, things that are, to me, very interesting, that there's still work being done, still questions to be answered. And then I'd like to also talk about my idea for FWS having its own cosmic ray detector. So, uh, so what are cosmic rays? High energy particles that are traveling through space and traveling at a very high fraction speed of light, like 99.99 something percent of the speed of light. So very high energies, composed of mostly protons and antiprotons. So of those, mostly protons. That's about 90% of them that hit our atmosphere. Electrons and anti-electrons, that's about 1%. Ions of of atomic nuclei. So basically from helium on up is about 9%. Most of those are helium, and it kind of drops off quickly after that. But heavier elements of the periodic table are bombarding our atmosphere. And then some of that, as I've kind of said, antiprotons, anti-electrons. So some fraction of this is antimatter, and actually more than you might expect. And that's something else I'm going to touch on briefly. A very wide range of energies. I mentioned that very high fraction speed of light, but and something else I'll talk about here. Imagine just a single proton, a single particle with the total energy of a thrown baseball. So take all that, just one particle with the like billions and billions that fills up a baseball, and just that amount of energy squeezed into one single particle. So cosmic ray air showers, this is something I'm going to talk about here quite a bit. So okay, so cosmic rays, if we didn't have an atmosphere, we'd all be dead. Having all these high energy particles hitting us all the time. The atmosphere blocks most of them. So usually, typically what happens is when they hit the upper atmosphere, it'll create what's called an air shower. And so that's going to be composed of a primary particle. So that's going to be the particle coming in from outer space. And then it's going to create a shower of secondary particles. And as many of thousands, maybe even tens of thousands of particles could be generated from a single cosmic ray. This is the plots here are simulations from my good friend and former colleague, Glenn Sobrowski. And he shows 3 different types of particles there and the types of air showers, if you were taking this and flattening on a 2D surface, what that would look like from the ground. So secondary particles, all sorts of different interesting things pop out in the secondary particles in the air shower. So you can get electrons, positrons coming from that air shower, pions, neutrinos, muons. So all sorts of, if you're familiar with the standard model of physics, all sorts of different interesting things pop out of it, all sorts of different particles. The particle type and the energy of the primary will affect the size and shape of the air shower. And so this is used by a lot of experiments to determine what kind of particle it is and what energy it has. So we can learn a lot by just studying like the shape of these air showers. So these air showers are actually very important for this field of study. So muons are, I have a whole slide on actually, but they're essentially heavy electrons. So they're a type of subatomic particle. Actually, they were first discovered with cosmic rays. That's something I'll talk about here in a second. So bear with me, Mark, and I'll get to that. How about that?
The mouse over the minimize on the like that.
What's happening?
Hiding them so we can see the slides.
Oh yeah. Okay. Yep. Yep.
See everything else.
So cosmic rays, 2 basic types of cosmic rays. The solar energetic particles. So this is our sun. Our sun produces a lot of cosmic rays. So I would say most of the cosmic rays do come from there, especially during solar flare periods. That's where you get a lot of them. These can be, a bit of a problem. They can disrupt satellites, and they can be a problem for communications on Earth. So, so during a solar flare, that could be somewhat problematic depending on how big the timing and the size and shape of the solar flare. A lot of what I'm going to be talking about here is going to be galactic and extragalactic cosmic rays. So these are things coming outside of our solar system. This is still very much an ongoing field of study. So the exact origin, where they come from in space, is still not very well understood. What'll happen is, because in the galaxy you have this magnetic field that pretty much exists between stars in interstellar space, and that kind of shuffles them up. You get particles deflected in a magnetic field, so it kind of scrambles their path as they're flying. So you really can't tell where they're coming from. So it's not like you can point a telescope and say, okay, the cosmic rays are coming from here. You need sort of a secondary process to figure that out. So that makes it a very difficult thing to figure out where cosmic rays are actually coming from. It's not as easy as just pointing somewhere and saying, oh, look, they're cosmic rays. So the lower energy cosmic rays are believed to be within our own galaxy, and they're most likely to be from supernova remnants or pulsar wind nebula, something that was in part of my thesis. And then the high energy ones are believed to be outside of our galaxy and most likely from active galactic nuclei or supermassive black holes. So by saying cosmic rays, we can learn more about these things and vice versa. So why would we care about cosmic rays on Earth? Well, for one thing, you get bit flips on electronics. So you have cosmic rays that make it through the atmosphere, penetrate all the way through the Earth, and they'll pass through the transistors and your electronics and your phones, what have you, and they will sometimes flip a bit. So you have binaries. So sometimes you get things in binary will flip from 0 to 1 or vice versa. So that could, depending where that 0 and 1 is, that could really mess things up. So, and of course in space, something I have to be concerned with working at L3 Harris is how do you deal with this with a space instrument, with something that's flying on orbit? And so oftentimes we'll use what's called triple modular redundancy, or TMR, or radiation hardened circuits to prevent this from happening on orbit, which have been fairly successful. And then even with the atmosphere coming through, sometimes you get these random stray one that just gets through. And I don't know if anyone here likes video games, but there's an example of someone doing a speed run of the video game Super Mario 64, which is a game I've not played. But in 2013, I guess it caused Mario to jump really high, basically teleporting to an area he couldn't get through. And everybody was like, and there's a video on this on YouTube. So, and eventually it was like there was a whole investigation about what happened in this video game, and ultimately it was decided it was a cosmic ray. So another useful thing that you can do with cosmic rays is muon scattering tomography. So this is a relatively new field. This has only been happening for like the last 10 years or so. So muons, which are, as I mentioned, are essentially heavy electrons, they'll interact in low density material more than they will in high density material. So the thicker something, more dense something is through the more penetrating it is through lower density material. And so this is an alternative to X-rays, essentially. So you can generate imagery with this than more so than X-rays. And so you can do really interesting things like this, and I'm not an archaeologist, but there was this paper that came out a while back about finding voids, new areas in the pyramids, Khufu's pyramid, by using this technique. So you can learn all sorts of new things. It's basically a new way of imaging using cosmic rays. So something that we get basically for free on the Earth's surface. And they were also, the Fukushima nuclear reaction, it was also used as a part of that investigation back in 2011, I believe it was. So another interesting thing that happens with cosmic rays is what's called astronaut's eye. So astronauts, I think this was first reported by the Apollo program. Astronauts will sometimes in space see random bright flashes of light when they're outside the magnetosphere. And this is manifested in all sorts of different ways, different shapes, different colors. And this is widely believed to be a result of cosmic rays. So you have like a cosmic ray, just a point here, cosmic ray is essentially flying through someone's eye and creates essentially a cone of light through various methods here. It looks like different ways to do it, depending on, I guess, the shape and what you actually see. So yeah, you can fly in space and see things you normally wouldn't with cosmic rays. So moving a little bit into history. So basically the began the field started with Victor Hess in 1911. The existence of radioactivity was known, but it was confusing because they kind of expected radiation coming up, radon and other things in the ground coming up, and they were observing the opposite. They were saying, okay, wait, the radiation gets higher the further up we go. What's going on here? So Victor Hess, pictured here in the balloon, he would go up and he would take instruments and hot air balloons, and he would measure radioactivity as a function of how high he was, at great risk to himself. So I think the field owes a lot to he came through it okay, but not exactly the most safe thing to do, and probably couldn't get away with that today. And the conclusion of these measurements he did is that this radiation was actually coming from space. And this result was later confirmed by another scientist, Robert Millikan. And he was the one who coined the term cosmic rays. And Hess won the Nobel Prize in 1936 for this. So if that comes up on Jeopardy, you know the answer to that one now. Antimatter was first discovered using cosmic rays, as I mentioned earlier. So Paul Dirac in the 1920s, he was the one who first theorized that antimatter could exist. Carl David Anderson, who was a student of Robert Millikan, who I mentioned on the previous slide, he was the one who actually made the discovery following up on his work with cosmic rays. And what he was doing is essentially the image here is a bubble chamber. And he was measuring the paths that the particles would take. And the paths were the opposite of what he expected to be of a particle traveling in a magnetic field. So he realized something's going on here with the same mass, but opposite charge. So that's effectively what antimatter is. So same mass, same charge, but opposite charge. So opposite sign of charge. And so Carl David Anderson, he shared the Nobel Prize in 1936 with Victor Hess.
Was that chamber in a laboratory or on a balloon?
I believe it was in the laboratory. Yeah. Yeah, I don't think you can take this up in a balloon. So other discoveries in cosmic rays. So in the days before we had the Large Hadron Collider and Fermilab and these big particle acceleration experiments, we made a lot of discoveries using cosmic rays. So something that we were getting essentially for free, just being bombarded by the atmosphere. So in 1936, the muon was discovered. In 1947, the pion were discovered, both using cosmic rays. Air showers were later discovered, I don't have a date here, but I think this was like the late 50s by Bruno Rossi and Pierre Auger. Then measurements in the 1950s also, so because of the air showers, they were able to measure the energy in the rival directions of the cosmic rays for the first time. 1958, the Van Allen radiation belt was discovered. So it's essentially this radiation belt that trapped solar cosmic rays that could be a difficult thing to navigate if you're up in space. You want to avoid that. 1961. I always feel like I have to include a pop culture reference. Fantastic Four #1 comes out. From Marvel Comics. The Fantastic Four get their powers from cosmic rays. Don't do this. Don't try it. So arguably, I don't know, this might be when cosmic rays enter the mainstream, or at least, people, I'm sure many people aware, kids reading comic books in the 60s, become aware of the existence of cosmic rays. 1991, the oh my God particle was discovered. The funny thing is when you get higher up in energies, you get fewer and fewer particles So we get high enough energies, you can actually start naming them because you get like single digits. The oh my god particle is the highest energy particle ever detected. And I'll talk about that when I get into other experiments later. 2021, the Amaterasu, my Japanese is really rusty, the Amaterasu particle, which is a particle of similar energy, was discovered. So cosmic ray detection experiments, because there's so many different types of energies of, as I mentioned, all different types and energies that, so because the field is so diverse, so is the methods for detecting them. So I'm going to talk about a few the ground-based instruments. I've actually trimmed this list, so this list is not completely accurate anymore. But but there's ground-based instruments such as Veritas, where I used to spend my time. Space-based. There's a cosmic ray detector actually located on the International Space Station. There's actually a few, but I'm just going to talk about AMSO2, Fermi-LAT, Voyager. The Voyager probes, which have gone beyond our solar system, have cosmic ray detectors. I'll talk about that a little bit. And then there's a whole bunch of different balloon experiments. Even after Victor Hess, did his balloon experiments, people are still doing. They're not actually going up on. It's all anime now, so people aren't actually going up in balloons and measuring cosmic rays anymore. But so the Pierre Auger Observatory. So this is located in the prairies of western Argentina. This is an instrument specifically designed to find the highest energy cosmic rays. So they're, as I said, they go into, they get very rare as you go up higher and higher energy. So a particle detected by Auger occurs once per square kilometer per year. So it's a very low count rate. If you go even one order of magnitude, it's even lower than that. So 10 to 20 EV events occur once per century. So these are but you spread that over a large area. So the larger area, you can get better detection rates. So Auger has these water tanks. One of them is pictured here. 1,600 tanks squared across about 1,100 square miles. So it's a huge area. So there's two different. So there's the water detectors, which I believe that's a water detector there, and then there's also UV light that's given off by cosmic rays. That's they have a secondary system for that. Yeah. So Cherenkov going through the water tank. Yep, exactly. So few more fly's eye and telescope array. Both of these are in the western Utah Western Desert, Utah. Fly's Eye is no longer in operation. That was 1981 to 2006. Telescope array is the successor to that, which I think started right when Fly's Eye ended, so in 2006. So it's even smaller than Auger. So this is about 270 square miles. Still pretty big. So like Auger, it has two different types of detectors, but the technology is a little bit different. The UV detectors are similar to Auger, but they, instead of water tanks, they have scintillators, essentially. So big sheets of plastic, essentially, that detect the particles as they pass through them. So the oh my god particle was discovered by Fly's Eye in 1991. So this is 3.1 times 10 to the 20 EV. This is the highest energy particle ever detected. Okay, so next I want to talk about a little bit about IceCube and KM3Net. So these are neutrino telescopes. So what's a neutrino? Neutrinos are pretty much known as ghost particles. They're very, very tiny. There's a lot of them. Basically, if you spread out your hand like this, about 1 billion are passing through your hand about every second. So they pretty much permeate all matter. They're just around us all the time. So in order to see anything from a neutrino telescope, you pretty much have to get a large vat of stuff, for lack of a better word. So in this case, Ice Cube is underneath the ice under Antarctica. So they drill holes into the ice in Antarctica, and they use ice basically as shielding to try to get the neutrinos to stop and give off light, which these circular detectors here, these guys, they're called DOMs, will pick up the brief flashes of light, again Cherenkov light, given off by the neutrino interaction. So Ice Cube is under the ice in Antarctica, and KM3 is in the Mediterranean Sea. So that's one way of detecting the secondary showers from cosmic rays is using these guys, neutrino telescopes. I want to, just a sidebar, I want to get a friend of mine here who actually used to, he still does actually work for Ice Cube, and he's been down Antarctica a few times, so I keep trying to convince him to come and give a presentation for us, so hopefully, he's a busy guy though, so it's a little hard to track him, but hopefully I'll get him to do a full presentation on this someday. So AMS-02, this is on the International Space Station. AMS stands for the Alpha Magnetic Spectrometer. It was launched on the Space Shuttle Endeavour back in 2011 and then attached to the International Space Station. AMS is basically a very big, very high-powered magnet. And so you get a very large, you kind of see the coils of the detector here, of the magnet here. And you have particles that enter and they get flung around by the magnetic field of this very large and very powerful magnet. And they're using that, you're able to make out the energy and what type of cosmic ray you're looking at. As I've said in my, one of my first slides, it's mostly protons, but elements up to iron on the periodic table have been detected with AMS. The neat thing is I went to their website as I was making this presentation, and they actually have a counter. They actually have a tracker. 260 billion cosmic rays have been detected by AMS as of a few days ago, February 15th when I was explaining it. Huh? Oh, is that trillion? Yeah, no, it's trillion. Yeah. No.
No, you're right. Billion.
Billion. Yeah.
Million, thousand.
Yeah. Yeah.
Many.
Mark's throwing me off.
Many.
Many. A lot. A lot of cosmic rays have been detected by AMS. Huh? I really should have. Yeah. Because that's the way it's presented on the webpage, so I wanted to show the full number like that. But cosmic ray detectors on Voyager 1 and Voyager 2. So we have cosmic ray detectors now left the solar system. Both Voyager 1 and Voyager 2 have a what's called a CRS, which is a cosmic ray subsystem. So each CRS on each Voyager has 2 high-energy telescopes, 4 lower-energy telescopes, and an electron telescope. So in 2018, when Voyager 2 left the solar system, it was used to determine that the sun, it actually left the sun's heliosphere, that's sort of the protective bubble created by ionized particles from the sun. After however 40-ish years, 40, the 50 years now, that Voyager 1, Voyager 2 have been active, they're still going strong. So Voyager 2, the heater was turned off as I understand, as you get further away, the power demands become greater. So as part of a power saving scheme, the heater was turned off, so the CRS on Voyager 2 is not as effective as it used to, but it's still going. And here's Voyager, and the cosmic ray detector is over here. And so I'm not going to read off the whole list of science objectives here, but you can just tell here there's a lot. Measure the energy spectrum of electrons, the spectra and elemental compositions of nuclei as you get further away from Earth to outside of the solar system now, and these plots show Voyager 1 and Voyager 2 as the big diff here in this graph here is when they leave the heliosphere, so the counting rate goes way down as you leave. So, and as they were flying by Jupiter and the other planets, learned a whole bunch of information about the particles, the cosmic ray environment in that area. So,
why does it fall off like that?
So basically, the solar system's in like a big productive bubble, and it's leaving that bubble. So that drop in the rate is leaving the productive bubble, the heliosphere.
So it's solar particles inside that.
Right. Yeah. Yeah.
So they're just scattering out more? What's
It's like a giant torus, I believe. So it's just like kind of flowing out and flowing around. Yeah.
Thanks.
Yep. So balloon experiments. There's many different balloon experiments. So take your detector, build a detector, and put it on a high altitude balloon. Sounds like fun. So this is how you're able to build a very specialized instrument for cheap, basically. So if you're a PI and you have a good idea, you can do this relatively cheaper than putting something on, say, the International Space Station or building a large ground-based array of telescopes. I've tried in putting together this presentation to come up with like a complete list of balloon experiments through the years. I couldn't do it. There's just like so many I couldn't count. So I'm just going to list off a couple examples here, and personal bias here because I actually know people who work on these ones. So GAPS was one that launched from Antarctica in December 2025. They were searching for anti-deuteron particles, so it's like a isotope of helium, I believe. So this is something that if you find them, it could be a signature of dark matter annihilation. Helix was used to measure the boron to carbon ratio, which may not sound super exciting, but it's actually very useful for cosmic ray propagation models. So as I mentioned, that particles get deflected around in the interstellar medium by magnetic fields. So understanding that boron to carbon ratio helps understand those models a little bit better if we can get that number, that ratio refined a bit. And that was launched from Sweden in May of 2024, and that flew for 6 days and 8 hours and eventually landed in northern Canada. Of course, I have to talk about Veritas. This is where I used to spend my time. I was a researcher on this experiment for a couple of years. Many years, over a decade actually. Also did my PhD thesis on these telescopes. So Veritas is the Very Energetic Radiation Telescope Array System. This is used to design to detect Cherenkov radiation generated by gamma rays. So gamma rays, like cosmic rays, will also create air showers in the upper atmosphere. So it's because it's essentially a very similar technique for finding cosmic rays. We also get cosmic rays. As we get the cosmic rays for free, they're after our background. It's actually kind of annoying, but we get all this sort of free information that's background. It's normally data we throw away, but some of us had the bright idea of like, okay, let's do something with these fields we're not using. Four telescopes for gamma rays measure gamma rays from 80 GeV to about the 30 TeV. Angular resolution is 0.1 degrees, which sounds lousy, but actually for a telescope this type is pretty good. It's located in the southern Arizona, USA. It's about 100 scientists in the US, UK, Ireland, Germany, and Canada. And started in 2007 and still going.
So Ben,
Yeah.
how do you measure gamma rays? You get Cherenkov radiation from gamma rays?
Yeah. So it's a very similar process to the cosmic rays. So they'll also interact in the upper atmosphere, create a very similar shower, and so but gamma rays don't get deflected by a magnetic field. So you point at the gamma ray source, and yeah. So Veritas is designed to detect gamma rays, but I mentioned we get electrons and other cosmic rays for free. I was actually talking to Paul coming in here if this counts as AI or not. But this was well over a decade ago, so if it is AI, it's a very early version of it. But essentially, as I mentioned, gamma rays and electrons and other cosmic rays create the same types of showers, and the differences between a gamma ray shower and an electron shower actually look very similar. So there's very essentially very small differences. So essentially we used what's called boosted decision trees, which is a type of machine learning to pick out the electrons from the other showers. And so this plot here shows BDS response. So every particle that was detected by Veritas got a BDT response. And so anything close to the 1 on this graph is more electron-like, and then anything at -1 is more proton-like, essentially. So you do this, and you train your machine learning, and then you get a spectrum out of it. And so the blue points here are the Veritas spectrum of electrons. Technically, it's electrons plus positrons. So because Veritas can't distinguish between electron from positron, they all look the same to us. So this is technically electron plus positrons here, but it's dominated by the electrons. So here shows the blue points is the Veritas, the red as a fit to the data, and the black points are other experiments that have also measured electrons. So you can see that the Veritas spectrum agrees pretty well with the other experiments. The key feature in the spectrum is there's a break here about 700 GeV, and the reasons for this break are still not well understood. It's believed that as you move up in energy, you're moving from one population of cosmic rays to another, or different things generating cosmic rays, so a different population of cosmic ray sources from one to another. But which ones, we're still not sure. So there's still active things going on there. And Veritas has done other cosmic ray measurements, but maybe save that for another day.
What visible wavelengths are you looking at?
So the Cherenkov light itself is in the UV, but we use the UV information to construct the energy of the gamma ray, and the gamma ray goes up to gamma ray energies. So it's actually, technically it's a UV detector, UV to optical, but yeah, falls up about 400 nanometers, I think. Moving on to basically science mysteries with cosmic rays, things that are still not understood, areas of ongoing research. The origins of high energy cosmic rays, as I mentioned, they're still not well understood. The low energy ones is pretty well understood. That's most likely to be from the sun. As I mentioned, that cosmic rays get deflected around, moved around, scrambled by the magnetic fields between stars. So it's really hard to pinpoint where exactly they come from. But it's pretty much, so the spectrum here, and this is a spectrum of all different particles mixed together, essentially. So this is an all-particle spectrum. And you can see several different features in the spectrum. So so there's a knee energy here, and then what's called an ankle energy out here. And so it's believed that below the knee are galactic sources. So we believe that these are supernova remnants or pulsars or pulsar ring nebulae that are generating these. And then once you get above the knee energy, we think this is a transition into extragalactic fields. So this is again, intergalactic nebulae, supermassive black holes, the center galaxies, that sort of stuff. Possibly starburst galaxies. So like M81, if you guys are looking at messier objects, that's been one that's been theorized to be a source of cosmic rays. Electrons and positrons lose energy quickly, so we believe that anything, this is dominated by the protons and the heavy nuclei. Electrons are a very small fraction of this, and we believe that because electrons and positrons lose their energy faster than the positrons do in the heavy ions, We believe that any electron sources of cosmic rays are relatively close by and within like 1 kiloparsec of the Earth. So, and it's why experiments like Veritas are useful, because unlike cosmic rays, gamma rays don't get deflected by a magnetic field, so they point exactly at their origin. So you point your gamma ray telescope at, and gamma rays and cosmic rays, for the most part, have similar processes being generated. So, so if you have a gamma ray signature, then there's a high likelihood of having a cosmic ray signature also. The very highest energy, so above the ankle energy here, so way out here, the things like the oh my god particle exist what's called above this ankle energy, and these ones are really not understood well at all. In fact, they shouldn't even theoretically exist. There's a theory, a cutoff called the GZK cutoff, and GZK are for 3 scientists, which I don't remember the name of anymore. But it's just abbreviated the GZK up cutoff. The proton above this energy should interact with the cosmic ray, the cosmic microwave background, and create pions. So they shouldn't even reach the Earth. They should we shouldn't even be receiving them. So the oh my god and the Amaterasu particle are above this cutoff, as well as a handful of others. I think there's been maybe 10 or 20 that have been detected above this energy. So last thing I want to talk about before I talk to you about my proposal here is the positron excess. So this plot shows the fraction of positrons to electrons. So anti-electrons to normal electrons. At higher energy, actually what is being measured, and here it shows 3 different instruments measuring this, the fraction is higher than anticipated. So this black line here on this graph is what the models and the theory expect to happen. And then here's what's actually seen. We're actually seeing that fraction rise with energy. So as you go higher and higher energy, you're actually seeing more anti-electrons than you might expect. And the reasons for this are still not certain, and AMSO2 and other various balloon experiments are still looking into this. Heat was a balloon experiment, and Pamela, I believe, was a satellite. And so there's kind of 2 leading theories for this, and you go to a scientific conference on cosmic rays, and you see a lot of heated discussion on this. But the 2 leading theories are this is evidence for dark matter annihilation. So that's 70% of the matter known in the universe could be causing this that we have not yet seen, or a large hidden pulsar is also theorized to produce these positrons in this number. So it would take a lot of pulsars to see this, though. So there's essentially a large hidden population of pulsars somewhere in our galaxy that we haven't detected yet. So either way, to me, it's very interesting. So finally, I just want to conclude here with my idea for the club for a cosmic ray detector. And so why should we do it? Well, I think it's awesome. I'm biased. I will admit it. I will freely admit being biased. I think it's a good rainy day activity. Let's face it, we live in Fort Wayne. We have a lot of those. I think this would be a good educational activity. I think this would be a good opportunity for club members of all ages to learn more about particle physics and particle detectors, learn about cosmic rays, learn more about electronics and soldering, learn a little something about programming, and mechanical engineering and 3D printing. So, and then actually, after we finish it, I think this would be a good opportunity to educate both members and the public. And, I hope I've convinced at least some of you that this is a wonderful and fascinating topic of study. So, and again, I admit this is my personal bias. What's a muon? That's already been asked. So muons are essentially heavy electrons. So here we have the standard model of particle physics, Higgs boson being the newest one here. So here's the muon down here. So they're the same charge and spin as electrons, but about 207 times more massive. So muons are inherently unstable, though. So they decay about 2.2 microseconds after they're created. So they don't actually live that long.
Gamma rays fit in there at all? They're not.
Gamma ray is a photon, so
It's a photon.
it's a photon. Yeah.
Where's the oh my god particle?
It's well, we actually don't completely know what the oh my god proton is, but we think it's probably a proton. So that'd be a combination of whichever quarks make up a proton, which I don't remember anymore.
It's under quarks.
It's under quarks, yeah. It's more likely to be a quark.
There's a gamma.
Combination of quarks.
So it is fun.
How are muons created? I don't want to dwell too much on this, but because I already talked about air showers a bit. But you have cosmic rays that bombard the atmosphere, and it creates these showers of secondary particles. You get one particle that will create two particles. Each one will have half the energy of the primary, and so on it goes. So each generation will lose more and more energy, and many of the, here's all the different particles that will come out of an air shower, and here are muons down here. If you hold out your hand like this, you get about 1 muon per second passing through your hand. So that's fun fact. So that tells you about what sort of area we'd have to deal with for building a detector. So muons will pass through a thick piece of plastic that's called a scintillator. The muon will scatter out the particles that make up the scintillator. That will create tiny flashes of light in the scintillator, which will be picked up by a silicon photomultiplier, which will lead here to a readout and a detector. And really what we want to do is we want to have two of them, and we want them as a coincidence, so this would help cut down on any potential background signal. So it's like you see one, it could be fluctuation, it could be statistics, something maybe wrong with your detector, but if you get two within pretty much the same time, roughly the same arrival time, then there's a very, very high chance that you've detected a muon. So I think we can probably, the simulator part of it, I think could be 3D printed. I think I need to look into more on that. I'm not too familiar with 3D printing, so.
Jim is, though.
Jim is, yeah.
And Dale.
Yeah, and Jim's already said he's on board, so. Alternatively, I think, maybe do both here, but we could do a cloud chamber. I think Sarah's has some experience with this. You get supersaturated alcohol vapor, and this is used to visualize. I think this is really cool. Something I remember when I was still in high school, I would go to like physics open houses, and they have demonstrations of these. And so you get some dry ice and a cloud of vapor essentially, and you can actually see the tracks of particles. And this is how Anderson discovered the anti-electron, the positron. Pretty proven technology here. So both muons and positrons have been discovered using this pretty much this exact same method. So here's a little thoughts on organization. I detest the idea of being called any sort of project manager. So title I picked for myself is head muon wrangler. Looking for a few people. Here's what I'm kind of thinking about organization. Maybe 2 to 4 people working on the electrical, the soldering components, 1 or 2 programmers. I'm not sure which languages, maybe Python or C++, for computer integration calibration. 1 to 2 people working on a mechanical structure. 1 to 2 people doing like 3D printing of the simulation material. And then, if we have, some extra people and we want to build a cloud chamber, we've got a few people working on that. And I shouldn't say that if you volunteer to work on this that you should be doing one thing. There could be definitely overlap if people want to try different things, depending on volunteers. And really, I want to make this for all skill levels. I want beginners welcome. I think this is a good opportunity for. I think elementary school is maybe a little bit too young, but middle, high school, undergrads in STEM fields, or just anyone who's interested in learning a new skill. Just some thoughts on the project needs and partnerships. I need a workspace. So I don't know if we want to actually set aside a bench at the observatory for this. Doesn't seem quite fitting. Tech venture. I've looked into them a little bit. Do I need to clear out some space in my garage? I could do that. Budget, there's the website Cosmic Garage Project. They claim they can build a muon detector for less than $100. I'm very skeptical of that, to be honest. But I'm thinking $500 can probably get us most of the way there. Maybe more if we decide to also build a cloud chamber. And the first $500 I'll pay out of pocket, and then we'll go figure things out after that. Timeline. Those of you who know me personally know that I've been working hard, and I've been on business travel quite a bit in Southern California. Don't feel sorry for me. So I've been on business travel quite a bit. I'm glad to be back here this week. So it's probably going to continue for most of the spring, I'm thinking. So hopefully when this winds down, I can get serious about this. So I think this spring, I'm just kind of looking for volunteers, interests. And then, summer, fall, I think we kind of get people together and, talk about it, get a sort of research phase going. Maybe get some meetings, at StarQuest or elsewhere. And, figure out, what design we want to go, which way we want to figure out who's going to do what. Maybe get started this fall and winter, start building, especially, if it's fall, winter. We're probably not going to be outside looking through telescopes, and so we're probably going to have lots of cloudy days in which you do this. And then it finishes when it finishes. I don't know how long it's actually going to take, so. That's pretty much my presentation, so I hope you enjoyed it. I hope you learned some stuff. Yeah, Peter?
Do you have a diagram of what you want to build?
I got links to various websites here.
How big is it, and where do you want to put it?
It's probably about a bread box-ish. Like it's not too terribly big.
So you want to install it indoor or?
I mean, it's portable. It'd be portable. It's like we'd get you just plug into an outlet actually, and you can just take it to the observatory or wherever.
What's the downside of the observatory? I can think of only a couple. You have to put your things away if it's summertime. So
Yeah.
you can do observing. You have to have a project box or cabinet to store.
Okay. Well, I mean, we
it's
can.
kind of out of the way. That would be the other.
It's a little out of the way, and then I mean, I guess my thought is I didn't know if there was really the space, but
Well, we can move chairs and get them.
Okay.
Out there.
All right.
Space.
Okay.
Your garage is not bad.
Well, for computer, I was thinking get a Raspberry Pi to do that. Huh? Oh, there we go. John, how did I know that I was going to be able to count on you on this?
Actually, started giving them away. I started using like x86 stuff.
Let's talk.
The garage means that you have to be home for it to work, which is
I know.
a huge problem. And in the interim,
Well, I'm hoping my travel will wind
we
down.
need to do some fundraising.
I mean, I honestly don't know what kind of budget I'm going to need here, but
Fundraising level, we should be able to collect some money at our public outings and things. We need to talk about that more at the next board meeting, how we're going to actually do some fundraising, because the big blue rehab is going to need a couple of $100, and this needs $500. I mean, we should be.
Well, like I said, the first bit of it, the first part of it, I'll pay out of pocket. I'm okay with that.
Well, you don't have to. We can fundraise it, and anything we don't come up with.
Okay,
Yeah.
I can make out the difference, sure.
We need to figure out how to do that, and we need to get better at it, what we're not doing now. So we need to walk a little bit, crawl a little bit, then walk a little bit.
Okay, well, we can talk about the board meeting.
Yeah, absolutely.
Okay, so that's pretty much my presentation. So I've been kind of answering questions as we're going here, but anything else? Yeah.
Are there any theories on how these particles get going almost the speed of light?
Yeah, so there's a whole branch of study involved with that, but essentially it depends on the type of objects doing accelerating. So here, for pulsars, it's essentially like you have the very intense magnetic fields. So you have synchrotron radiation that's basically pair producing. So that's creating particles that way. For the active galactic nuclei, I'm not as familiar with but there's a whole branch of story. There's a whole ton of theory papers on depending on which objects you think are generating the cosmic rays. There's a whole bunch of different models out there for that.
All right.
Yeah, the jets. Yeah, jet acceleration.
Anything else? If not, thank you, Ben.
Yeah. Thank you, guys.
Very sorry for all of the difficulties we had setting up in the audio problems that came even later to cause us more trouble. Did anybody bring any images that they'd like to share? All right. Come on down. Let's see what we have to disconnect here. Ooh, this could be a problem.
You don't have a USB?
Yeah, well, we do, of course, but we're out of ports. You think if I'm going to destroy the audio here for a second.
My flasher.
We're going to have to reconnect the audio. We're going to have to stop sharing.
Well, we don't need audio.
I think it already reset.
Did it?
Yeah, it gave a
Oh, good.
notice.
Stop sharing. There we go.
Where am I?
Jim, can you hear us? We good?
Yes, I can hear you fine.
We're
Thank
fine.
you.
Now we have to find sharing, and then we have to find.
Hey, Jim,
Yeah?
Yes.
Dennis had a question, but he says he can't talk. So, if he can send you a message, maybe.
Here we go. Let's see.
Okay.
Photos. And I'd be on the other end here.
Tulips?
Wait a minute. Oh, that's 20. Go down there. My bad.
You want the top?
Yeah. Oh, where is it?
Wait a minute. Hang on. All right, here we go.
It
You
should
want
be
that
20,
way?
26.
26.
All the way to the bottom, it's date modified. The date's getting longer the further down you go.
Now it should be at the top.
I hope.
26.
Yeah.
Oh, there.
Is that what you want?
Yeah, I think so.
And then
There
I
you
think
go.
if we share. All right. Jim, you seeing the Horsehead Nebula and the Flame Nebula?
No, I see a directory.
Okay, we're not sharing the right thing then. Hang on.
You probably just have to click on that or something, or you're sharing the wrong thing or something.
Yeah, it's sharing the wrong thing. How about now?
Yeah.
Okay. And if we do that, do you see a different one?
There, that's.
Yep.
That's the one.
All right.
It's darker.
Peter, all you have
More
to do
contrast.
That was it.
is click on the
That
this
was
if you
all.
want to move off.
That was the only one I had that I wanted to
You
show.
want to explain what it is, what kind of camera it was, and how
that
your
was-
image processing, please?
That was 2 nights ago with my 6-inch Ventura f3.8. And we finally got a clear night. A bunch of us met out at the observatory Friday night. Ainsley's were there, Ed was there. And of course it nicely clouded over right at 6:30, even though it had been clear all day long.
Yeah, it was clear all afternoon. It cleared when I left.
Did you stay long enough till it got clear?
9:30.
Oh, okay, because when I got home about 9, it was clear in my house. So, anyway, that was Sunday night.
How long
Okay.
of an exposure is it to then?
That's the Horsehead
Uh,
Nebula.
about
The
20
dark,
minutes,
the dark one is the
15
Horsehead
seconds.
Nebula.
Is the Left-Hand Star in Orion's
Yeah.
belt?
Right, so this is the Horsehead, this is the Flame Nebula right here,
Right.
and I forget what this is, and this star is the westernmost star of Orion's belt.
Aratak or something like that.
I don't know the name of it, I forget. It's, I don't think it's a binary, but it could be. There's a binary, I think, down in here with all this nebulosity.
Okay.
Go full screen, or is that?
Is it what?
You mean like that?
Yeah.
That was the original, and I did some adjustments on it.
Yeah, really sharpened it up.
Yeah.
I think the flame looks
How
like
long
the
is exposure is that?
What's wrong with it, Ed?
No, I was gonna say the flame to me looks like Scooby-Doo. They asked how long the exposure was to be, what was that?
They were 15-second exposures for about 20 minutes total.
Did you post-process?
Yeah,
Well,
that's what
you
the
saw it
difference
there.
in the two images is.
What did you use for post-processing?
Process one.
I just used the Apple. Okay, just the Apple stuff.
The Apple app?
Yeah. Well, no, just the Apple Photo.
So since the Flame Nebula is so close to the one of the bright stars in Orion, one of the keystone stars, you actually don't need anything but your telescope. A dial will allow you to find it if you have enough aperture, which apparently isn't much, and you have the sky to support it, and your eyes are young enough to where you can actually see it. You don't really, a filter would help, like an O3, but it's not actually required. So if you can see the Flame Nebula visually, you have half a chance to see the Horsehead visually. And around here, I don't think I've seen the Flame Nebula for anything but brief little tendrils here and there, not a really good view of it, so it makes it really tough if you're not imaging.
Ed and I were able to visually see the Horsehead one night, but it was with my 16-inch Dob
Right.
and his light intensifier.
Yeah, no, I've seen it years and years ago under darker skies that we have, this Bortle 4 that we have.
Right.
The image scale is a little bit tough, unless you got, like, say, a larger scope or whatever it is.
Yeah.
Because the Horsehead is really kind of very small.
I've always thought it to be kind of large, but you're right. But the problem is that visually you don't see it as black on a red.
Right.
You see it as black in a really charcoal gray kind of a field, and it makes it really difficult because there's no contrast. Very, very, very poor contrast. So it's a real challenge.
Right.
People down in Florida have claimed that they could see it with binoculars, which I've never believed.
It's pretty big, but it's.
Yeah. Anyway, so that's what you had, okay? I'm
Okay.
going to stop sharing.
Yeah.
All right. Anybody else? Thank you, Peter.
I got a little thing.
Go right ahead.
Okay. Okay. Well, I've been messing around with the Sea Star. You guys can hear me, I'm assuming, right?
Yes,
Okay.
and we see your M51.
Yeah. I got an M51, but the cool thing is that I've been having some issues with um, drop frames and all that stuff on the Sea Star. I got 109 minutes, and a couple of them I'm not getting any drop frames. And there's a reason for that, is that the equipment that I bought from Skywatcher has got like a shoe with a Vixen style like V wedge, and it just simply screws into the side, and so it tends to cock the thing at an angle, and then it puts there's a pin that it puts, and it actually contacts the underside of the Sea Star And as the sea star's trying to find stuff, it actually unscrews the sea star, so you don't get real good astronomy. So this is another one. Yeah, I'm still getting some issues here, but and then this is what is it, M100. So I got to do some post processing. But the second thing I wanted to talk about real quickly was what the heck is going on mechanically. One of the issues is this is a sea star in CAD, and I didn't have to model it. Somebody else did that for me. But this circle is the center of gravity of the sea star, and this is the center of the tripod. But normally, when you set this thing up, this center of gravity is way over here, so I got to hang a weight off of this side. So I kind of come up with a couple of innovations. First is I got my own clamping system here, and see if you can see that can, as the I can clamp along the whole length as opposed to having a screw going in here, and it basically makes it kind of cockamamie. And then I'm thinking of two ideas. One is I got a hinged plate, and then I'll have a screw here. But notice if I move this, I can slide it back and forth depending on your latitude. I could extend this, and the center of gravity is always going to be over the center of the tripod, so I don't need a weight, right? Which is pretty cool. And let me see, there's another option. Yeah, we'll
Is
put
that
this
3D
one in.
printed, Jim?
Huh? No, it'd
Is
be a
that?
piece of metal, and
Oh, what?
I'd have to fab it, but it's
Yeah.
it's just quarter-inch aluminum or something. It's pretty easy. I could do it in the shop. Um, this material over here, the shoe is also going to be aluminum, but I'm probably going to either have Dales or somebody 3D print it, and then there's some tricks you can do. You can take the 3D printed part and you could actually cast it in metal by making a mold from it in sand or something. So anything we can 3D print, let me see what I'm doing here.
You could sell it with the
Uh,
coffee cups.
yeah, I mean, we could make metal coffee cups. Just think of it.
No, no,
Uh,
for your.
well, anyways, the second design is you move this and it stays bolted here, but as this rotates here, we'll still keep the center of gravity here. So this is like design B. So I'm going to get off the screen, but I just thought you guys would be interested in that. So, you know, a lot of the problems with that scope is it was never intended as a equatorial. All right. Thank you.
Thank you, Jim.
Yeah. See if I
Anybody?
can un.
Oh,
What was that for? What was going on?
they liked your presentation.
Really? Okay. I thought they were just happy that I shut up, you
No,
know?
you could take a bow. Was it because you wanted him to be quiet? I misunderstood. I'm sorry.
Thank
I didn't mean to
you.
mislead you, Jim.
All right.
Anyone else?
Got a quick question for Ben.
Yeah, I got to come back up.
I,
I
I
don't
guess
have portable
what
microphones.
I guess an observation also. Um, we out in Zoom land, we could not hear probably 90% of anybody that was in the audience. So any questions that were asked, we totally missed. I mean, we could hear you, Ben, but we out in
Right.
Zoom
Well,
land
guys,
missed missed it.
I'll apologize for that. I'll take the hit for that. The
Yeah.
wireless microphones that we had did not work, and we were really unable. We didn't have any backup for it today. If things had run normally, we would have had backup, and everything would have been a lot better.
No,
So
just
next time, I'm going to bring my own video camera like we have now from the center, and we'll have at least some backup. But as far as being able to get the audience, that's going to be difficult without having working wireless microphones. So we'll have to work on figure out why why it failed tonight, and it did fail pretty badly.
No,
Yeah.
So
it's just a,
apologize for that, but not much we could do.
no, I just
Sorry.
wanted just to explain that out here we probably don't have a lot of questions and comments for Ben because we couldn't hear things. But Ben, fascinating discussion, and not really related exactly to what you're talking about, but you made a comment about the neutrinos, and I was kind of interested in that. Is it true that the vast majority of neutrinos passing, say, through the Earth are generated in our sun?
Yeah, that's correct.
What, if you had to take a stab, what percentage or what number are not generated by our sun that may, say, impinge on the Earth?
I'm going to say that's actually probably still not well understood. I think that's maybe still an open science question, actually, if I remember correctly. Shot in the dark, 10% less. Like
Okay.
I think the vast majority are generated by the sun. Yeah, but
Yeah.
I think it's similar to cosmic rays in that the highest energy neutrinos are believed to be originating outside of our solar system, outside the galaxy. So there was a paper, made a big splash in the community back in 2018 where they found a ice cube detected an event which coincided with a gamma ray blazar going off at exactly the same time. So that was like very interesting to the community, and I think Ice Cube doesn't have the greatest angular resolution, but I think it was somewhere in the vicinity of that area too. So that sparked a lot of interest in thinking that maybe these high energy neutrinos are generated by AGN, active quasars, active galaxies.
Yeah. It's fascinating. And I'm just really sorry that we had the audio glitch and we missed a good deal of your presentation. So I don't know. I raise my hand and vote that maybe you do a repeat presentation, because
Oh well,
I thought it was fascinating, and I'm
yeah.
just kind of sorry that we missed a good deal of it.
I mean, with the audio issues we've had and interruptions, yeah, I'm available to that.
Oh, we have three open ones.
Thank you very much.
Oh, okay, well, yeah. All right.